A quiet assumption has guided human thought for centuries, that reality is singular, sealed, and self-contained. Space stretches, time flows, matter obeys its rules, and the universe unfolds within invisible but trusted boundaries. Yet modern physics has begun to whisper a dangerous possibility, that those boundaries may not be walls at all, that reality itself may be porous. This opening chapter frames the central mystery, evidence suggesting that another reality, another physical domain governed by its own laws, may be intersecting with ours. Not metaphorically, not philosophically, but physically, measurably, and perhaps repeatedly. The hook unfolds through unsettling imagery, unexplained cosmic scars, impossible temperature asymmetries in the cosmic microwave background, gravitational effects with no visible source. The narration emphasizes unease rather than spectacle, an intrusion so subtle it escapes intuition, yet vast enough to reshape cosmology. The chapter establishes emotional stakes by confronting a core fear. If realities can overlap, then the universe is not a closed system. Cause and effect may not begin or end where humanity assumes. The laws of physics may be local customs, not universal truths. This opening does not yet explain. It unsettles, framing the mystery as a slow realization rather than a sudden shock, preparing the viewer for a journey where certainty dissolves and reality itself becomes a question. The idea did not arrive as a revelation. It emerged slowly, quietly, carried on streams of data meant to answer far more modest questions. At the end of the 20th century, cosmology was not searching for other realities. It was attempting something almost humble by comparison, to measure the echo of creation itself with greater clarity than ever before. In 1989, NASA launched the Cosmic Background Explorer, COBE, into low Earth orbit. Its purpose was precise and restrained: to map the cosmic microwave background, the faint thermal afterglow left behind when the universe cooled enough for light to travel freely, roughly 380,000 years after the Big Bang. This radiation had been detected decades earlier, its existence a triumph for Big Bang cosmology. COBE's task was to measure its uniformity, to confirm that the early universe was smooth, predictable, and well-behaved. Instead, COBE revealed something unsettling: tiny fluctuations in temperature, differences of only 1 part in 100,000, etched across the sky. These irregularities were not noise. They were real, and they mattered. They represented the primordial seeds from which all galaxies, stars, and planets would eventually form. The universe, it seemed, had never been perfectly uniform. Even at its beginning, it carried subtle imperfections. At the time, this discovery was celebrated as a triumph. The data aligned beautifully with inflationary cosmology. The universe had expanded rapidly, stretching quantum fluctuations to cosmic scales. Structure arose naturally from randomness. The story appeared complete, but precision has a way of sharpening questions rather than settling them. In 2001, the Wilkinson Microwave Anisotropy Probe, WMAP, took the measurements further. Orbiting the Sun at a stable gravitational point, WMAP observed the cosmic microwave background with far greater resolution than COBE. It mapped the sky again and again, refining the temperature variations, tracing the geometry of space itself. From this data, cosmologists calculated the universe's age, composition, and curvature with unprecedented confidence. Yet buried within this clarity were features that resisted explanation. The most famous was a region that came to be known as the cold spot, a vast area of the sky, significantly cooler than surrounding regions, spanning an angle far larger than inflationary models comfortably predicted. It was not a single pixel anomaly. It was an extended structure, large enough to be cosmologically significant, persistent across datasets. At first, instrumental error was suspected, foreground contamination, statistical fluke. Each explanation was tested and stripped away. The cold spot remained. By the time the European Space Agency's Planck satellite launched in 2009, expectations were high that lingering uncertainties would finally dissolve. Planck was designed to be definitive. Its detectors cooled to fractions of a degree above absolute zero. Its sensitivity unmatched. It mapped not only temperature, but polarization, subtle orientations in the cosmic microwave background light that carry information about the universe's earliest moments. Planck confirmed what earlier missions had hinted. The cold spot was real. Large-scale asymmetries were real. The universe, on its grandest scales, was not behaving as a perfectly random, statistically uniform system. One hemisphere appeared slightly different from the other. Power was distributed unevenly across scales. Alignments emerged that had no obvious cause within standard cosmology. None of these anomalies alone shattered the prevailing model. Together, they formed a pattern that was difficult to ignore. Meanwhile, another line of investigation was unfolding far from the quiet vacuum of space. In the realm of theoretical physics, researchers were grappling with equations that refused to fit neatly into 4 dimensions. String theory, developed to reconcile quantum mechanics with general relativity, required extra spatial dimensions to remain mathematically consistent. Not optional dimensions, necessary ones, curled tightly beyond direct observation, or extended in ways unfamiliar to human intuition. Within these models emerged the concept of branes, multidimensional surfaces on which entire universes could exist. In some versions, all known particles and forces were confined to a 3-dimensional brane embedded in a higher dimensional space, while gravity alone could move between realms. In others, multiple branes floated parallel to one another, separated by distances imperceptible to conventional measurement. These ideas were not philosophical speculation. They were consequences of equations. Attempts to preserve internal consistency in theories descended from Einstein's work on spacetime and Hawking's explorations of cosmic boundaries. As inflationary theory evolved, it too began to imply multiplicity. Eternal inflation suggested that once inflation began, it never truly ended. Instead, it continued in regions of space, spawning bubble universes, each with its own physical constants, its own histories. Most remained forever isolated, but collisions between bubbles were not forbidden. Such collisions, theorists realized, might leave imprints. Distortions in the cosmic microwave background, temperature anomalies, circular patterns, asymmetries frozen into the fabric of the observable universe. It was here that 2 paths began to converge. Observers stared at maps of ancient light, puzzled by structures that resisted conventional explanation. Theorists examined equations predicting interactions beyond a single cosmic domain. Neither side was searching for confirmation of the other. Yet slowly, cautiously, parallels emerged. Could the cold spot be the scar of a collision with another universe? Could large-scale anisotropies reflect influences from beyond our cosmic horizon? Could gravitational effects attributed to unseen matter instead hint at interactions across dimensions? Such questions were not embraced easily. Extraordinary claims demand extraordinary evidence, and cosmology is haunted by statistical coincidences that vanish with improved data. The scientific community remained divided. Alternative explanations persisted, supervoids along the line of sight, rare fluctuations amplified by chance, incomplete modeling of early universe physics. Yet none fully satisfied. What made the moment remarkable was not consensus, but restraint. Papers appeared on AR-14 exploring multiverse signatures, brane collisions, and higher dimensional gravity, not as declarations, but as possibilities constrained by data. Observational teams refined analyses, searching for patterns predicted by theory without presuming their existence. The language of science remained careful. No proclamations of discovery. No confirmation of intersecting realities. Only an acknowledgement that the universe appeared slightly stranger than expected. Einstein once warned that nature is subtle, but not malicious. The anomalies did not shout. They whispered. They did not overthrow physics. They nudged it quietly toward deeper questions. By the early 21st century, cosmology stood at an unusual threshold. Instruments had grown precise enough to reveal imperfections once lost in noise. Theoretical frameworks had grown expansive enough to accommodate realities beyond direct observation. Between them lay a narrow, unsettling possibility. that the universe humans inhabit may not be entirely alone. Not separated by vast distances of space or time, but by dimensions, fields, or boundaries barely understood. That the data collected to map the birth of the cosmos might also be recording faint echoes of something else, another structure pressing gently against the limits of observable reality. The discovery phase did not end with certainty. It ended with alignment. Observation and theory, once distant, now gazing toward the same horizon. Not claiming what lay beyond it, only recognizing that the horizon itself might not be the final edge. Physics has always been built like a fortress. Its walls are conservation laws, its gates guarded by locality and causality. Energy cannot appear from nothing. Forces act through space, not across it without mediation. Effects follow causes, sealed within the same reality that produces them. For centuries, this structure has endured assaults from paradox and mystery, yet it has never truly cracked. Even the strangest discoveries, black holes, quantum uncertainty, the warping of space-time, ultimately reinforce the walls rather than breaking them. The suggestion that another reality might intersect with this one struck at the foundation itself. The shock did not arrive with a single paper or announcement. It accumulated slowly, like stress fractures spreading through stone. Each anomaly was small, defensible in isolation. But together, they began to challenge assumptions so basic that they were rarely spoken aloud. Conservation was the first to tremble. In cosmology, energy accounting is not straightforward, but it is relentless. Every observation must fit within the universe's balance sheet. Yet gravitational effects were appearing without visible sources. Galaxy clusters bent light more strongly than their luminous matter could explain. This discrepancy was attributed to dark matter, an unseen component inferred through its gravitational pull. Dark matter became a pillar of modern cosmology, supported by rotation curves, lensing maps, and structure formation models. And yet, even with dark matter included, certain lensing patterns refused to align perfectly. Some mass distributions appeared distorted in ways that did not match simulations. These were not dramatic contradictions, but subtle mismatches. Residuals that remained after models were refined and parameters adjusted. In most sciences, such residuals fade with better data. Here, some persisted. Energy presented a similar discomfort. The accelerating expansion of the universe, discovered through supernova observations in the late 1990s, demanded a new component, dark energy. A form of energy intrinsic to space itself, driving galaxies apart faster over time. The simplest explanation fit Einstein's cosmological constant, a term he once introduced and later abandoned. But its measured value was unsettlingly small compared to predictions from quantum field theory. Off by more than 100 orders of magnitude. It was as if energy were leaking, diluted, or regulated by something not accounted for within known physics. Locality, too, came under strain. Quantum mechanics had already wounded classical intuition, allowing correlations across distance through entanglement. But these effects, strange as they were, did not transmit usable information faster than light. Relativity remained intact. Cosmological anomalies posed a different question. Large-scale correlations appeared across regions of the universe that should never have been in causal contact. Inflation was designed to explain this, stretching once near regions far apart. But certain alignments, the so-called axis of evil in the cosmic microwave background, hinted at preferred directions. The universe, on its largest scales, appeared to have a subtle orientation. Such an orientation had no obvious cause within a closed, self-contained cosmos. Then there were patterns that felt imposed rather than evolved. The cold spot did not resemble the random fluctuations inflation naturally produced. Its scale and coherence suggested an external influence, like a dent pressed into space-time rather than a ripple emerging from within it. These ideas unsettled physicists not because they were dramatic, but because they were quiet. The equations did not scream impossibility. They whispered inconsistency. Causal closure, the principle that every physical effect has a cause within the same system, was the most deeply threatened. If anomalies were influenced by interactions beyond the observable universe, then causation itself might cross boundaries previously assumed absolute. Effects could have origins outside the cosmic horizon, outside spacetime as it is understood. This was not how physics was meant to work. The response was not panic. It was resistance. Papers proposing exotic explanations were scrutinized with exceptional rigor. Alternative models were pushed to their limits. Supervoids were mapped to explain the cold spot. Statistical variance was invoked. Modified inflationary potentials were tested. Systematic errors were hunted relentlessly. This resistance was not denial. It was discipline. Peer review became the arena where discomfort was expressed. Claims suggesting multiverse collisions or higher dimensional interactions were met with demands for falsifiability. Where are the unique predictions? What signatures cannot be mimicked by conventional physics? How does one distinguish an intersecting reality from an improbable fluctuation? These questions were not rhetorical. They were existential for the field. Einstein's shadow loomed over every debate. He had insisted that theories, no matter how elegant, must answer to observation. Space-time curvature was once an abstract mathematical idea. It became real when starlight bent around the sun during an eclipse. Black holes were once dismissed as pathological solutions. They became unavoidable once gravitational collapse was understood. Modern physics has learned repeatedly that reality does not owe intuition any loyalty. Yet the idea of intersecting realities felt different. It sounded metaphysical, even theological, despite emerging from equations written on chalkboards and validated against data from satellites. The language itself became a barrier. Words like other universe carried cultural weight that physicists instinctively distrusted. Still, the mathematics did not care about discomfort. In higher dimensional models, conservation laws are local, not global. Energy can be conserved within a brane while appearing to leak into higher dimensions. Gravity can spread across extra dimensions, weakening its apparent strength. Interactions between branes can transfer energy or imprint disturbances without violating deeper symmetries. Within eternal inflation, causal closure applies only locally. Bubble universes form independently, but collisions are permitted. Their effects propagate through spacetime, leaving scars that persist long after the event. These frameworks did not require abandoning physics. They required expanding it. The shock, then, was philosophical as much as scientific. Physics had long assumed that the observable universe, while incomplete, was representative of the whole. That the laws measured here applied everywhere. That the system under study was closed enough to be meaningful. Intersecting realities suggested otherwise. They implied that measurements might be influenced by conditions beyond observational reach. That constants could vary not randomly, but through interaction. That the universe might be part of a larger structure whose dynamics are only partially accessible. Such implications were not embraced lightly. Careers are built on refinement, not rupture. Yet the history of physics offers a pattern. Each time boundaries seemed absolute, they eventually softened. Earth was not the center. The galaxy was not the universe. The universe itself may not be singular. The shock did not destroy confidence in science. It tested its humility. What made this moment unique was that no new particle had been detected. No signal had been isolated beyond doubt. The disturbance existed at the level of interpretation, at the edge where data meets meaning. Physics was not collapsing. It was hesitating. In that hesitation lay its strength. The willingness to sit with uncertainty. To allow equations to suggest realities that feel implausible until evidence demands acceptance. To acknowledge that testable reality, as Einstein demanded, may extend beyond what can currently be tested. The shock was not fear of being wrong. It was the recognition that the universe might be more open than expected. That the walls of the fortress were not breached, but thinning, transparent enough to hint at something pressing from the other side. And in that pressure, subtle and persistent, physics encountered a question it could not yet answer. Only measure, model, and endure. The universe had not broken its rules. It had revealed that the rules might belong to a larger game. The initial shock did not end the inquiry. It refined it. When physics encounters discomfort, it does not retreat. It measures again and then again with greater care. If another reality truly brushed against this one, its influence would not announce itself loudly. It would linger in patterns, in statistics, in the quiet margins where data resists explanation. The Planck satellite became the central witness to this deeper phase of investigation. Launched by the European Space Agency, Planck was designed to complete what COBE and WMAP had begun, not merely to map the cosmic microwave background, but to exhaust its information. Temperature fluctuations, polarization modes, angular power spectra measured across the entire sky with sensitivity approaching theoretical limits. When Planck's full data release arrived, it did not resolve the anomalies. It refined them. The cold spot remained. Hemispherical asymmetry remained. Subtle alignments persisted across large angular scales. These were no longer artifacts of early instrumentation or incomplete sky coverage. They were embedded in the universe's oldest observable light, preserved since a time when matter and radiation were still coupled, when the cosmos was less than 500,000 years old. What troubled cosmologists most was not the existence of irregularities. Structure requires irregularity, but their coherence. Random quantum fluctuations, stretched by inflation, should produce patterns that are statistically isotropic, directionless, smoothly distributed in probability. Yet Planck's maps suggested something else. A faint preference, a gentle imbalance. As if the universe carried a memory not fully erased by expansion. Parallel to this work, large-scale structure surveys began mapping the universe in 3 dimensions. Projects like the Sloan Digital Sky Survey and later Deep Field surveys charted the positions of millions of galaxies, tracing filaments and voids that stretch across hundreds of millions of light-years. These maps revealed a cosmic web, vast tendrils of matter separated by enormous empty regions. Within this web, most patterns aligned beautifully with simulations based on dark matter and dark energy. But again, not all. Certain regions appeared statistically unusual. Voids larger than expected. Alignments that echoed features seen in the cosmic microwave background. Correlations between distant structures that strained assumptions of independence. These findings were subtle, debated, often contested, but persistent enough to warrant attention. The universe, when examined across different epochs and scales, seemed to repeat certain irregularities. Meanwhile, another frontier pressed inward rather than outward. Experiments probing quantum fields and vacuum energy deepen the mystery. According to quantum field theory, empty space is not empty. It seethes with fluctuations, virtual particles appearing and vanishing, fields vibrating even at absolute zero. This vacuum energy should be immense. Catastrophically so. Yet observations reveal something else. The measured energy density of empty space, dark energy, is astonishingly small. Stable. Uniform across cosmic distances. The discrepancy between theoretical prediction and observation is the largest known mismatch in physics. Attempts to resolve this discrepancy led some physicists to uncomfortable territory. Perhaps vacuum energy is regulated by physics beyond 4 dimensions. Perhaps what is measured is not the total energy of the vacuum, but the residue left behind after interactions with a larger structure. In higher dimensional models, vacuum energy can leak, dilute, or cancel through dynamics invisible to observers confined to a brane. This idea was not introduced to explain intersecting realities. It emerged as an attempt to save quantum field theory from contradiction. Yet it aligned disturbingly well with cosmological anomalies. As computational power increased, simulations grew more sophisticated. Teams modeled bubble universe collisions predicted by eternal inflation. They simulated how such events would imprint temperature gradients or circular features onto the cosmic microwave background. They compared these predictions against real sky maps, not searching for confirmation, but for exclusion. Some features matched. Not conclusively, not uniquely, but enough to keep the models alive. Brane collision scenarios produced similar signatures. When 2 higher dimensional branes interact, energy can be transferred locally, producing disturbances that propagate outward. These disturbances, frozen into space-time by inflation, could appear today as large-scale anomalies. Not sharp edges, but smooth distortions. Not violent scars, but gentle warps. What distinguished this phase of investigation was restraint. No single dataset was allowed to dominate interpretation. Each anomaly was tested against alternatives. Supervoid explanations for the cold spot were explored by mapping galaxy densities along the line of sight. Instrumental systematics were revisited repeatedly. Statistical methods were refined to account for look-elsewhere effects. And still, the anomalies endured. The patience of the process was itself revealing. In science, mysteries often dissolve with better resolution. Noise fades. Patterns clarify. Here, clarity did not eliminate strangeness. It localized it. The deeper the universe was measured, the more it seemed slightly misaligned with its simplest description. This realization did not convert skeptics into believers. It narrowed uncertainty. It suggested that if explanations remained incomplete, the fault might not lie in data quality, but in underlying assumptions. One assumption stood quietly beneath all models: the isolation of the observable universe. Physics had always treated the cosmos as a closed system for practical purposes. What lay beyond the cosmic horizon was irrelevant, causally disconnected. But if higher dimensions exist, or if inflation produced neighboring universes, then causal boundaries may not align with observational ones. Interactions could occur early, before horizons formed. Their effects would persist long after direct contact ended. Such interactions would not repeat. They would not be ongoing signals. They would be ancient fingerprints. This perspective reframed the search. Scientists were no longer hunting for active gateways or portals. They were studying fossils. Imprints left when the universe was young, malleable, and less compartmentalized than it is today. The convergence between observation and theory became increasingly quiet. Papers grew cautious in language. Phrases like consistent with and not excluded by dominated conclusions. Yet across AR-14 and conference halls, a subtle shift was underway. The possibility of intersecting realities was no longer dismissed outright. It had become one hypothesis among many, tested, constrained, and provisionally tolerated. What made the investigation compelling was not certainty, but resilience. The mystery did not retreat under scrutiny. It adapted. Each refinement sharpened its outline without fully resolving it. In the end, deeper investigation did not reveal another reality in the way a telescope reveals a galaxy. It revealed a pattern of tension between what is measured and what is expected, between theories that work beautifully in isolation and observations that suggest isolation may be incomplete. The universe, examined with increasing fidelity, seemed to carry subtle echoes of interactions beyond itself. Not loud enough to convince, not faint enough to ignore. Precision had not closed the case. It had narrowed it to a question of boundaries. Where does this universe end, and what, if anything, has already touched it before that end could be defined? At first, the anomalies could be treated as relics, frozen accidents from the universe's youth, sealed away by time and expansion. Ancient scars on a cosmos that had long since settled into isolation. But as theories matured and observations accumulated, a more unsettling implication emerged. If another reality had intersected with this one once, there was no fundamental reason it could not still be doing so. The mystery did not simply persist. It widened. In modern cosmology, the universe is not static. Space itself is dynamic, stretching under the influence of dark energy. Galaxies are not merely moving through space. They are being carried apart as space-time expands between them. This expansion is accelerating, driven by a force that remains profoundly unexplained. Dark energy behaves like a property of space itself, yet its origin resists every attempt at derivation from known physics. Some models began to ask a dangerous question. What if dark energy is not intrinsic to this universe alone? In higher dimensional theories, the expansion of a brane universe can be influenced by its environment. Pressure from neighboring dimensions. Energy exchange across boundaries. subtle curvature imposed from outside the familiar four-dimensional framework. In such scenarios, acceleration is not purely internal. It is responsive. If space-time can be stretched from within, it may also be tugged from beyond. This possibility reframes cosmic expansion as interaction rather than isolation. Dark energy becomes less like a constant and more like a signal, steady, uniform, but perhaps not self-generated. The measured value of the cosmological constant, so inexplicably small yet non-zero, begins to resemble an equilibrium rather than a fundamental parameter, balanced between competing influences, stabilized by physics that does not reside entirely here. The mystery deepens further when time itself enters the discussion. The arrow of time, the one-way flow from past to future, is among the most familiar features of existence, yet it is poorly understood at a fundamental level. The laws of physics are largely time-symmetric. They do not distinguish between before and after. And yet, the universe clearly does. Entropy increases. Structures form and decay. Memory accumulates in one direction only. Some cosmological models suggest that this asymmetry emerged during the universe's earliest moments. Inflation, rapid expansion, and symmetry breaking established conditions that favored one temporal direction. But if the early universe was not alone, if it was shaped by interaction, then time's arrow may carry an external imprint. In bubble collision scenarios, two expanding universes collide within a larger, inflating background. The collision is not destructive in the familiar sense. It is transformative. Energy redistributes. Fields realign. The geometry of space-time shifts. Such an event could bias the initial conditions of a universe, subtly altering how entropy evolves within it. Time, in this view, does not simply begin. It is tilted. Other models push even further. In certain higher-dimensional frameworks, what appears as time in one universe may be a spatial dimension in another. Intersections between realities could mix these roles in ways that defy classical intuition. Effects that appear temporally asymmetric from one perspective might be spatially imposed from another. These ideas remain speculative, but they are not arbitrary. They arise from attempts to reconcile gravity, quantum mechanics, and cosmology within a unified mathematical structure. They are constrained by consistency, not imagination. The escalation becomes unavoidable when these concepts are applied backward, toward the beginning itself. The Big Bang is often described as a singular origin, a moment when space and time emerged from an incomprehensible density. But many modern theories soften this image. The Big Bang may not be the beginning of everything, but the beginning of this universe's expansion. A transition rather than a creation. If so, what triggered it? In brane cosmology, the Big Bang can be modeled as a collision between higher-dimensional objects. Two branes approach, interact, and release immense energy. The resulting hot, dense state resembles a Big Bang without requiring a singularity. Space expands. Matter forms. Time unfolds. In eternal inflation, a similar role is played by quantum fluctuations in an inflating field. A region decays into a lower energy state, forming a bubble universe. That decay looks, from the inside, like a beginning. But if bubbles can collide, then the Big Bang may carry evidence of contact. Not merely expansion, but interruption. Not a pristine birth, but a shaped emergence. Some anomalies in the cosmic microwave background take on new significance under this lens. Large-scale asymmetries. Suppressed power at the largest angular scales. These could be interpreted as boundary effects, conditions imposed by a collision or intersection that preceded observable inflation. The universe's earliest light may not be a blank canvas. It may be a palimpsest. The emotional weight of this realization is subtle but profound. The universe, once imagined as a solitary unfolding, begins to resemble a shared environment. Not crowded, not chaotic, but not alone. This does not imply frequent interaction. On the contrary, if intersections occur, they are likely rare on human timescales. Separated by epochs longer than civilizations, longer than stars. But rarity does not equal irrelevance. Even a single interaction can shape everything that follows. And there is no guarantee that such interactions are confined to the past. In some models, branes drift. Distances change. Fields evolve. The geometry of higher dimensional space is dynamic. Intersections could be ongoing, slow, imperceptible except through their cumulative effects. A gradual influence rather than a sudden event. Physical constants, values assumed immutable, enter the discussion here. The strength of fundamental forces. The masses of particles. The rate of expansion. If these constants are determined by the configuration of fields in higher dimensions, then interactions could alter them. Not abruptly, but subtly. Over cosmic time. Such variation has been searched for. Astronomical observations test whether constants change across space or time. So far, results are consistent with stability. But the constraints still allow minuscule variation, far below everyday detection, yet cosmologically meaningful. The escalation is not toward catastrophe, but toward humility. The universe is no longer merely expanding into emptiness. It may be expanding within a context, one that includes other structures, other histories, other laws, interacting rarely, weakly, but enough to matter. This realization transforms the emotional landscape of cosmology. Awe is joined by unease. Not fear of destruction, but fear of misunderstanding. The fear that the universe's most fundamental behaviors may be influenced by conditions that cannot be fully observed or controlled. The sky becomes less like a boundary and more like a membrane. Throughout this escalation, science remains careful. No claim is made that another reality has been confirmed. No model has achieved decisive victory. The data does not compel belief. It permits possibility. But possibility, once permitted, cannot be unthought. The universe, viewed through this lens, is no longer a closed story written solely by its internal rules. It is a chapter in a larger volume. Its expansion, its timing, its structure potentially shaped by encounters beyond its visible edges. The mystery deepens not because answers multiply, but because the questions expand. What does it mean to exist in a universe that is not self-contained? What does it mean for causality, for explanation, for prediction? The fear is not invasion. There are no armies, no intentions, no agency implied. Only interaction without awareness. Influence without dialogue. In such a universe, humanity is not threatened. It is contextualized. And the cosmos, once imagined as a silent void, becomes something more intimate and more unsettling, a shared space, where even the most ancient light may carry whispers of neighbors never seen, never known, yet never entirely absent. When observation reaches its limit, theory begins its quiet work. Not to invent answers, but to stretch existing laws until they can accommodate what has already been seen. The ideas that attempt to explain intersecting realities did not arise from imagination untethered to evidence. They emerged from mathematics pushed to its breaking point, from equations that refused to close unless reality itself was larger than expected. One of the most enduring frameworks is brane cosmology. Its origins lie in string theory, an effort to reconcile Einstein's general relativity with quantum mechanics. String theory replaces point particles with one-dimensional strings whose vibrations give rise to particles and forces. For the mathematics to remain consistent, these strings must vibrate in more than 3 spatial dimensions. Extra dimensions are not decorative additions. They are required. Within this framework, the universe humans observe may be confined to a 3-dimensional membrane, or brane, embedded in a higher dimensional space known as the bulk. All familiar particles and forces are bound to this brane, unable to move beyond it. Gravity, however, is different. As the geometry of spacetime itself, gravity can extend into the extra dimensions, diluting its strength and explaining why it is so weak compared to other forces. This idea does more than address a technical problem. It offers a natural mechanism for interaction between realities. If multiple branes exist within the same higher dimensional space, they can approach, drift apart, or even collide. Such interactions would not resemble collisions between objects in space. They would be interactions between entire spacetimes, releasing energy, reshaping geometry, and imprinting disturbances that propagate within each brane. In some brane models, the Big Bang itself is not a singular origin but the aftermath of such a collision. Two higher dimensional surfaces meet, energy floods into the interaction zone, and an expanding universe is born. This scenario replaces an undefined singularity with a physical process governed by known equations extended into higher dimensions. Brane cosmology is not universally accepted, but it is mathematically rigorous. Its predictions can, in principle, be tested through cosmological observations, gravitational waves, or deviations from Newtonian gravity at small scales. It remains speculative, but disciplined. Another powerful framework arises from inflationary cosmology. Inflation was introduced to explain why the universe appears flat, uniform, and nearly isotropic. A brief period of rapid expansion in the universe's earliest moments smooths out irregularities and stretches quantum fluctuations to cosmic scales. This idea has been remarkably successful. But inflation, once begun, appears difficult to stop. In many models, inflation is eternal. While it ends locally, forming a universe like this one, it continues elsewhere. Regions decay into lower energy states, creating bubble universes within an ever-inflating background. Each bubble has its own spacetime, its own laws, its own constants. Most never interact. But the mathematics does not forbid interaction. Bubble collisions are rare, but inevitable in an eternally inflating cosmos. When two expanding bubbles meet, their boundaries intersect. Energy redistributes. Fields realign. From within one bubble, the collision would appear as a disturbance in the early universe, potentially visible today as large-scale anomalies in the cosmic microwave background. This idea has been explored extensively in peer-reviewed literature. Simulations predict specific signatures, temperature gradients, circular features, asymmetries, that can be searched for in real data. None have been conclusively identified. Yet some observed anomalies are consistent with these predictions, keeping the hypothesis alive. Stephen Hawking played a pivotal role in shaping how such ideas are framed. In his later work, Hawking sought to tame the multiverse concept, proposing models that limit its wildest implications while preserving its explanatory power. His collaboration with Thomas Hertog explored how quantum cosmology could impose boundary conditions on inflation, reducing the infinite complexity of eternal inflation to something testable. Hawking was not endorsing intersecting realities as fact. He was insisting they remain within the domain of science. Quantum mechanics introduces a different, equally unsettling possibility. The many worlds interpretation suggests that every quantum event with multiple possible outcomes results in a branching of reality. All outcomes occur, each in its own branch. These branches do not typically interact. Decoherence isolates them, preventing interference and preserving classical experience. Yet, decoherence is not absolute. It is a process, not a barrier. In principle, under specific conditions, quantum branches could influence one another. This idea remains controversial and highly constrained, but it is not forbidden by quantum theory. Some physicists have speculated whether cosmological-scale quantum effects could leave residual correlations, anomalies that appear classical but originate from quantum branching. Such ideas are tentative and far from consensus. They are included not because they are likely, but because they demonstrate how deeply the question of intersecting realities penetrates existing theory. Across all these models, a common thread emerges. None require abandoning known physics. They require extending it. Einstein's legacy looms large here. General relativity replaced absolute space and time with a dynamic geometry shaped by matter and energy. This was once considered radical, yet it has been confirmed repeatedly, from gravitational lensing to black hole mergers detected by LIGO. Einstein himself was cautious, aware that his theory might be incomplete. Modern theories treat spacetime not as the final stage, but as one layer of a deeper structure. Quantum field theory suggests that fields are fundamental, with particles as excitations. String theory suggests that geometry itself emerges from more primitive elements. Inflation suggests that universes are processes, not objects. Intersecting realities are not an alien intrusion into physics. They are a consequence of taking its most successful theories seriously. Speculation in this context is not fantasy. It is the disciplined exploration of what equations permit when constrained by observation. Each model is judged by consistency, by falsifiability, by its ability to explain anomalies without introducing contradictions elsewhere. None of these theories claims certainty. They coexist in tension, competing, overlapping, incomplete. Their value lies not in declaring what is true, but in expanding what can be asked. The discomfort they generate is a sign of their seriousness. Physics has always advanced by confronting ideas that feel implausible before becoming unavoidable. The Earth moves. Time slows. Space bends. Particles exist in superposition. Each was once unthinkable. Intersecting realities may join that lineage, or they may fade as better explanations emerge. What matters is that they arise from the same commitment that has guided science for centuries, the refusal to ignore evidence simply because it challenges intuition. In the end, these theories do not depict a chaotic multiverse teeming with activity. They describe a cosmos governed by subtle interactions, rare events, and long timescales. A universe that may not be alone, yet remains governed by law. The speculation does not close the mystery. It frames it. Reality, as described by modern physics, is no longer guaranteed to be singular. Not because science desires it to be otherwise, but because the mathematics allows it, and the data does not forbid it. Between certainty and imagination lies theory. And in that narrow space, the idea of intersecting realities waits, neither accepted nor dismissed, but mathematically alive, patient, and unresolved. Speculation, no matter how elegant, is only tolerated in science when it submits to measurement. The question of intersecting realities has therefore moved from philosophy to instrumentation. Not because certainty is close, but because uncertainty has become precise enough to interrogate. Modern cosmology is now defined by its tools. Machines built not to confirm belief, but to strain reality until it reveals where theory bends or breaks. At the forefront of this effort stands the James Webb Space Telescope. Suspended far from Earth at the second Lagrange point, Webb is not designed to look for other universes. It is designed to see deeper into this one than any instrument before it. Its infrared eyes peer through cosmic dust and across vast distances, observing galaxies as they were only a few 100 million years after the Big Bang. These observations serve a subtle purpose. If the early universe carries imprints of external influence, distortions in structure formation, unexpected distributions of matter, deviations from predicted growth rates, Webb may see them, not as dramatic anomalies, but as statistical tensions. Galaxies forming too early, mass assembling too quickly, patterns that challenge the timeline predicted by standard cosmology. Already, Webb's early data has stirred debate. Massive galaxies appearing surprisingly soon after cosmic dawn. Structures emerging with a maturity that strains existing models. None of this confirms intersecting realities, but it reinforces a recurring theme. The universe often seems ahead of schedule, as if its initial conditions were more complex than assumed. Alongside light, gravity has become a new messenger. Gravitational wave observatories such as LIGO and Virgo have opened a channel once thought permanently closed. They listen not for photons, but for ripples in spacetime itself, disturbances caused by merging black holes and neutron stars. These waves pass through matter almost unimpeded, carrying pristine information about violent events across the cosmos. Some higher dimensional theories predict subtle deviations in gravitational wave propagation. Energy leakage into extra dimensions could alter waveforms. Resonances could appear. Propagation speeds could deviate minutely from expectations. Future detectors, such as LISA, planned for space-based observation, will measure gravitational waves across longer timescales and lower frequencies, where such effects may be detectable. Again, the search is not for spectacle. It is for discrepancy. Cosmic neutrino observatories offer another window. Neutrinos are nearly massless particles that rarely interact with matter. They stream across the universe from supernovae, active galaxies, and perhaps even the Big Bang itself. Because they interact so weakly, neutrinos preserve information from extreme environments inaccessible to light. Some models suggest that interactions between realities could influence neutrino behavior. Altered oscillation patterns, unexpected energy distributions, deviations from symmetry. Facilities like IceCube in Antarctica and future neutrino detectors are refining measurements to unprecedented precision, searching for anomalies that cannot be reconciled with known physics. On Earth, particle accelerators probe reality from the opposite direction, downward into the smallest scales. The Large Hadron Collider was not built to find other universes. It was built to test the standard model of particle physics. Yet its collisions reach energies where extra dimensions, if they exist, might reveal themselves indirectly. Missing energy events, unexplained momentum loss, deviations in particle decay channels. These are the subtle signs physicists monitor. If particles can move into extra dimensions, even briefly, the accounting of energy and momentum would show discrepancies. Thus far, none have been conclusive. But the constraints themselves matter. Each non-detection narrows the space where intersecting realities could exist. Precision experiments also target the stability of fundamental constants. The speed of light, the fine structure constant, the ratio of particle masses. Observations of distant quasars and atomic clocks on Earth test whether these values change across space or time. Even minute variation would signal physics beyond the standard framework. So far, constants appear remarkably stable. Yet the limits allow for changes so small they would accumulate only over cosmic time. Stability does not guarantee isolation. It may reflect equilibrium. The cosmic microwave background remains under continuous scrutiny. New statistical methods are applied to old data. Polarization maps are refined. Foreground contamination is modeled with increasing sophistication. Researchers search for non-Gaussian features, preferred directions, and correlations predicted by bubble collision and brane interaction models. The process is iterative and slow. Each claim is tested against null hypotheses. Each pattern is challenged by simulations designed to replicate it through chance alone. This is not caution for its own sake. It is necessity. What defines this phase is humility. Science no longer asks whether another reality exists in a dramatic sense. It asks whether the universe behaves exactly as expected under the assumption that it is alone. When it does not, science does not leap to conclusions. It sharpens its questions. There is an understanding now, quietly shared across disciplines, that absence of evidence is not evidence of absence, particularly when the phenomena under consideration operate at scales beyond direct access. Intersecting realities, if real, would not announce themselves with signals designed for human comprehension. They would influence boundary conditions, initial states, rare correlations. Testing such ideas requires patience measured in decades. Future missions promise refinement rather than revelation. Next-generation cosmic microwave background observatories will improve sensitivity by orders of magnitude. Gravitational wave networks will triangulate sources with precision unimaginable a generation ago. Particle physics will push energies higher and measurements tighter. What emerges from this effort is a changed relationship with uncertainty. Physics no longer assumes that every mystery will resolve into a single, clean explanation. It accepts layered answers, partial truths, models that work within domains yet fail at boundaries. The possibility of intersecting realities has reshaped scientific temperament more than scientific consensus. It has reinforced the idea that understanding may always lag behind observation, that the universe may remain partially opaque, not because it is unknowable, but because it is larger than the frameworks built to describe it. The ongoing testing is therefore not a countdown to confirmation or refutation. It is a discipline of listening, of attending to small deviations, of allowing data to speak even when it says something uncomfortable. The instruments continue to operate. Data continues to accumulate. Papers continue to argue, refine, retract, and revise. No declaration has been made, no threshold crossed. And yet, something has changed. The universe is no longer treated as a sealed laboratory. It is treated as a system whose boundaries may be provisional, whose behavior may be influenced by conditions beyond immediate observation. Science proceeds not by certainty, but by constraint. Each experiment narrows possibility. Each measurement reduces ignorance without eliminating mystery. In that narrowing space, the question of intersecting realities remains, not as a belief, not as a conclusion, but as a hypothesis disciplined by instruments, governed by data, and held open by humility. The tools do not promise answers. They promise better questions. And for now, that is enough to keep listening. In the end, the instruments fall silent. The equations pause mid-thought. The data resolves into probability instead of proof. What remains is not an answer, but a perspective, quiet, unsettling, and expansive. If reality is not singular, then existence itself becomes contextual. Humanity may inhabit only one layer of a larger structure, a thin membrane of laws and constants stretched across something deeper and more complex. A domain where physics behaves consistently enough to build stars and minds, yet not necessarily exclusively. What feels complete from within may, from beyond, be only a region. For most of history, the universe was assumed to be everything by definition. There was nowhere else to be, no outside to imagine. Even when space expanded beyond Earth, beyond the solar system, beyond the Milky Way, it remained one connected stage. Vast, but unified. Modern cosmology has complicated that simplicity. Inflation theory suggests space itself may have grown in separate pockets, each cooling into its own universe with distinct properties. String theory allows for multiple solutions to the equations of reality, each corresponding to a different vacuum state. Quantum mechanics introduces the idea that outcomes branch, not collapse, leaving behind a multitude of coexisting histories. None of these ideas were born from mysticism. They emerged from attempts to reconcile observation with mathematics. Yet together, they imply something profound. Reality may not be a single story, but a collection of contexts, parallel, adjacent, or layered, each internally coherent, yet unaware of the others except through faint pressure at the boundaries. If so, then existence is not defined solely by what is observed, but by where observation occurs. Human beings evolved to survive within one narrow slice of possibility. The senses register a small band of electromagnetic radiation. Time is experienced in one direction. Space appears three-dimensional. These are not universal truths. They are local conditions. The realization is both humbling and destabilizing. To exist, in this view, is not to occupy the center of reality, but to occupy a coordinate within it. A location defined by physical constants, cosmic history, and boundary conditions set long before consciousness emerged. Everything familiar, matter, energy, causality, may be features of a particular region, not properties of all that is. This does not diminish meaning. It reframes it. If reality is layered, then significance is not derived from uniqueness, but from participation. A universe does not need to be alone to matter. A life does not need to be singular to be meaningful. Meaning arises from relationships, between particles, between forces, between moments in time. Even now, human existence is relational. Life depends on the nuclear reactions of distant stars. Consciousness depends on fragile chemical balances. Memory depends on time's arrow. None of this is isolated. All of it is contingent. The possibility that other realities exist does not negate this contingency. It deepens it. There is also unease. If other realities press against this one, even subtly, then the universe is not a sealed container. It is an interface, a place where boundaries exist, not walls, where influence may be indirect, statistical, or rare, but not impossible. The cosmic microwave background becomes more than a relic. It becomes a surface. Gravitational waves become more than signals. They become messengers that might, under extreme conditions, carry traces of interactions beyond their source. Quantum randomness becomes more than ignorance. It becomes the imprint of deeper structure. Yet no evidence has confirmed this. And science, disciplined and restrained, does not ask for belief. What it offers instead is a shift in posture. Humanity no longer stands before the universe as a puzzle to be solved completely. It stands within it as a phenomenon shaped by conditions it did not choose. The ambition is no longer total comprehension, but alignment. Models that work, predictions that hold, questions that refine themselves over time. This humility is not resignation. It is maturity. The history of science shows a pattern. Each time reality was assumed to be complete, it expanded. Earth was not the center. The sun was not unique. The Milky Way was not alone. The visible universe was not all that existed. Every expansion was first resisted, then integrated. The possibility of multiple realities fits this pattern, not as an ending, but as another widening of the frame. Still, uncertainty remains. There may be no way to observe other realities directly. Their influence may be too weak, their separation too great, their interactions too subtle to isolate from noise. The universe may be shared in principle, yet opaque in practice. If so, the question becomes philosophical rather than empirical. What does it mean to be alone? Aloneness, traditionally, implies exclusivity, that nothing else exists beyond the known horizon. But in a layered cosmos, aloneness may mean something different. It may mean isolation without absence, separation without emptiness. Humanity may not be alone in existence, yet entirely alone in awareness. That idea carries both comfort and sorrow. Comfort, because meaning does not depend on cosmic exclusivity. Sorrow, because connection may be impossible even if proximity is real. Other realities, if they exist, may be closer than distant galaxies and still forever unreachable. There is no violation in this. Nature is not obligated to satisfy curiosity. Yet curiosity persists, not because answers are guaranteed, but because wonder is intrinsic. The impulse to look beyond the horizon is not driven by reward. It is driven by alignment with something deeper, an instinct to situate existence within a larger pattern. The universe, in this view, becomes not just vast, but shared. Not just mysterious, but relational. A structure in which layers coexist without awareness, like voices in separate rooms of the same building, each speaking a complete language, each unable to hear the others. And perhaps that is enough. Perhaps the value lies not in crossing the boundary, but in recognizing that one exists. In understanding that reality may be richer than experience suggests. That certainty is local. That mystery is not failure, but context. The unanswered question remains suspended. Are we alone in our reality, or simply unaware of who else is touching it? No experiment has closed this question. No observation has resolved it. It lingers not as an absence of knowledge, but as a presence of possibility. Science continues its work. Telescopes collect photons. Detectors listen to space-time. Equations evolve. Constraints tighten. But beneath all of it lies a quieter realization. Existence may not be singular. And if it is not, then being here, now, within this particular set of laws, is not diminished by what lies beyond. It is defined by it. A moment, bounded yet meaningful. A layer, complete in itself. And a universe that, whether alone or shared, continues to invite attention, not with promises of answers, but with the enduring gravity of unanswered questions.